All right, this video we're going to talk about thermochemical equations. So we're actually going to talk about energy and chemical reactions rather than just physical change. So similarly, we can transfer the energy from a reaction to water and figure out the energy that the reaction released or absorbed. So imagine burning gasoline, which is octane, and then transferring its energy to water. Then water is going to warm up as it gains that energy. So if we're going to figure out how much energy the water gained, since the water warmed up, we'll use Q equals mc delta T. Now we're interested specifically only in the water. So we'll use the mass of the water, the specific heat of the water, which is liquid, and the delta T of the water, which would be 82 degrees. So this tells us the water gained 134,121 joules, or 2 technically, or 134.12 kilojoules. And it gained it from the gasoline burning, the octane. So how much energy did the octane release? That same amount, it would just be negative. Okay. But usually when we talk about like how much energy a reaction releases or absorbs, it's usually like per mole of something reacting. So we do need to know how many moles of octane burned. We only burned 2.6 grams, and we want to convert that to moles. Now, a little bit of review. Octane is an alkane, and we can figure out how many H's it has by taking its number of carbons, doubling it, and adding 2. So that would be 18. So the molar mass is 114 grams per mole. So we only burned 0.023 moles of octane. So when we talk about the heat of a reaction, how much energy is released, we want to look at the energy per mole. So this is how much energy was released when only 0.023 moles reacted. I want the energy per mole. So anytime you see per, it's like divided by. So we're going to take the energy that was released divided by how many moles have reacted. And this will give us that we've released 5,880.6 kilojoules per mole of octane burn. All right, so if you guys remember, the energy released per mole of something, or absorbed per mole, that's a delta H in kilojoules. So we're going to call this the delta H specifically for the reaction of octane burning. So we have heats of fusion. We use those for melting and freezing. We have heats of vaporization. We use those for boiling and condensing. But we also have heats of reaction that communicates how much energy is either absorbed or released per mole of reaction. So how we're going to incorporate that into a reaction, like a written out, for example. Remember that reactants are written on the left. That's what goes in. Products are written on the right. That's what comes out. We can incorporate this heat in 2 different ways. One, I can simply just write it on the side. So write heat of reaction is negative 5,880.6 kilojoules per mole of octane released, which is per 1 mole. Or I can incorporate this literally as either a reactant or product, depending on whether it's endo or exothermic. So think about the heat is negative. Is that endo or exothermic? That means it's negative. That means it's exothermic. Energy is released. So if you think about what's released, is it reactants or products? So think about release is exiting, it comes out. That means energy is technically can be written as a product, something that is released or comes out of a reaction. So you'll see that I'll write that we not only make water and carbon dioxide, but we also make 5,880 kilojoules of energy. So note that by writing it as a product, I do not have to show a negative symbol, because by writing it as a product, I'm assuming that energy is exiting already. That's what the negative implies here if you write it on the side as a delta H equals. So either way implies that energy is released. Okay, now another thing that we can do with this heat is we can actually use it in stoichiometry, dimensional analysis, to convert, like, what if we don't have a full mole of octane burning? What if we only have half a mole of octane burning? Like, how much energy does that release? Obviously half that amount. Or what if we burn 0.1 moles of octane or 50 grams of octane? How much energy is released? We can use this as a conversion factor to find that. So let's see on the back. Okay, so same reaction. I have that here. Okay, so we can just look at that. For example, how many grams of oxygen would be used up if this much energy is released when we burn octane? So we always start with the number that they give us in the problem. Write down its unit kilojoules, because we know that that is what's going to have to cross cancel. And in the end, we want to get to grams of oxygen. Well, the delta H, the heat of reaction, says that 5,880 kilojoules of energy is released when 8 moles of carbon, I'm sorry, we're looking at oxygen, when 12.5 moles of oxygen reacts. So we want to put the energy term on bottom so that the units cross cancel, and the 12.5 moles of oxygen on top. So it's kind of like using a mole ratio, except part of that mole ratio is energy. All right, now we want to get to grams of oxygen. Well, every 1 mole is 16 grams, or sorry, 32 grams, since it's O2. And then we can solve. So that means 9,929 grams of oxygen has to react to produce this much energy. All right, let's look at it another way. How many joules of energy is released when 1.96 grams of carbon dioxide forms? Okay, so again, start with what they give us, 1.96 grams of carbon dioxide. Note that we want to get to joules of energy in the end. So how am I going to do that? Well, the reaction says that for every 8 moles of carbon dioxide that reacts, we release 5,880 kilojoules of energy. I can't use that yet because I'm in grams, so I'm first going to have to convert grams of CO2 to moles. And every 44 grams are in a mole. Then we can use this from the reaction. Every 8 moles of CO2 is going to release 5,880.6 kilojoules of energy. You can stop here, get your kilojoules, and then put it into joules, or you could just say, do it all in one. Every 1 kilojoule is 1,000 joules. Okay, so that means we release 32,744 joules of energy. Okay, so that's for exothermic reactions. Let's look at a cold pack. So a cold pack, if you know, you have to activate it, you have to squeeze it, and that breaks a pouch of water, which then allows it to mix with the solid in the other pouch, ammonium nitrate. And when it mixes, it gets cold. That means it's taking energy from your hand, which is the surrounding. So if energy is going from your hand to the cold pack, and the cold pack is taking in that energy, that means it's endothermic. I can also tell it's endothermic because it's a positive delta H, which means like money is entering your bank account, right? It's positive on your statement. Delta H is positive. Energy is entering the reaction. So what this reaction says is that 25.41 kilojoules of energy is absorbed when specifically one, since there's a one out here, when 1 mole of ammonium nitrate dissolves. I know this process is endothermic, so if energy is entering, could I incorporate this as a reactant or product? The answer is reactant because that is what enters reaction. So another way of incorporating it would be like NH4NO3 solid plus 25.41 kilojoules of energy. We'll make NH4 ions and nitrate ions. All right, let's use it in stoichiometry. How many grams of ammonium nitrate must dissolve to absorb 100 kilojoules of energy? So start with 100 kilojoules. We know that kilojoules is what's going to have to cross cancel, and we want to get to grams of ammonium nitrate. Okay, the reaction says that 25.41 kilojoules is absorbed when 1 mole of ammonium nitrate reacts. But now I want to get to grams, so we have to use the molar mass. Every 1 mole is 80 grams. So it's 314.8 grams of ammonium nitrate that would have to dissolve. That's a lot. It's definitely more than what's in your cold pack. Okay. How many joules of energy is absorbed when 5 grams dissolves? So let's start with 5 grams. And remind ourselves we want to get to joules in the end. Well, the reaction says that 25.41 kilojoules of energy is absorbed when 1 mole reacts. But I can't use that yet because I'm in grams, so I have to convert my grams to moles first, and then I can use the fact that every 1 mole of ammonium nitrate reacted absorbs 25.41 kilojoules of energy. You can stop there, get your kilojoules, and just move the decimal to get it to joules. Or you can just say every 1 kilojoule is 1,000 joules. So this absorbs 1,588 joules. All right, try out this next one on your own. Maybe take a pause for a minute before I go through it. Okay, so I know this question isn't part of it. Lulu. My dog just found a toy in the closet. Sorry. Okay, so the heat of reaction is negative. So is that endo or exothermic? So think about money on your bank account. If it's negative on your statement, that means it left your bank account, it exited. It's exothermic. So would we incorporate that as a reactant or product? You could incorporate it as a product because that's what exits reactions are products. Okay, but anyway, if you have, Lily, get out of there. Start with 53.7 kilojoules of energy. And we want to get to grams of oxygen. The reaction says that this amount of energy is released when 3 moles of oxygen reacts. And I want to put the kilojoules on bottom. Technically, this would be -2. So that it cross cancels. So I made both of these negative because technically this is how much energy is released. It would be negative. So if I put one negative here and forgot it there, then your answer would be negative, which isn't possible. You can't have negative grams. All right, then every 1 mole is 32 grams. And you should get .3 grams of oxygen. Okay, so that's it for thermochemical equations. You guys can now use the rest of your time to finish the nail lab. If you were absent, I put data on a PowerPoint for you to view. Use that data, not someone else's. Or you could do the heat of fusion lab, the ice lab from yesterday. You can finish that up. Staple it to your partners and turn into the bin when you're done. And then if you're done with all that, then you can work on your homework.